Okay, so this is a quick introduction for iGCSE, section 2C, energy and voltage. It's called. It's really potential difference. Quantities and symbols you need to know. Current is the ampere, charge is coulombs, energy is measured in joules, power is watts or joules per second, resistance in ohms, time is seconds, and voltage, the volt, V, or potential difference. Quantities then, so it's joules are how we measure work or energy. So you've got 1 joule or 1 Newton meter when we apply a force of 1 Newton to an object to move it 1 meter. That's a joule. That's all it is. It's like moving an apple. You could think of a meter across a desk. The ampere, so we think of coulombs. So each little electron has a tiny bit of charge. All of it adds up. If we take 6.25 times 10 to the power of 18 of them, if all of those pass per second, we call it 1 amp or 1 coulomb per second. Resistance, that's a measure of how much a wire resists flow of current. You find it by the ratio of V divided by I is R, or V equals IR, via. And we measure it in ohms. Omega is the symbol. What did you say? Yes, the SI unit of power equivalent to 1 joule per second in an electrical circuit where the PD, potential difference, is 1 volt and the current is 1 amp. So P is VI, 1 watt is 1 joule per second. Equation-wise, similar ones to coming up before. So power, current times voltage. Energy transferred is current times voltage times time. We must convert to seconds. Energy in joules is also charge times voltage or potential difference, is QV. And we said about V equals IR already. Now, what's quite important is thinking about the formulas for series resistance and parallel resistance. So series resistance, the total resistance, you just add up the two resistors. But in parallel, 1 over, or the reciprocal of resistance, is 1 over the resistor 1 plus 1 over resistor 2. The key bit is, if the resistances are different, the current will be different in each branch. We've got some clever little rules for series and parallel circuits. So in series, the current's the same everywhere, but in parallel it splits according to resistance. In series, the PD, the energy is shared, whereas in parallel, the components on that branch get all the energy for the power supply. In series, we said the resistance adds up as a simple total down the bottom corner, or in parallel, it's lower. So if we have more pathways, we have a lower overall resistance. Sort of pictures like this between brighter bulbs, dimmer bulbs, that kind of thing. We need to know our component graphs. So we've got thermistor. So resistance versus temperature, it drops rapidly, non-linear. Same for light intensity. So similar idea with these symbols. Non-ohmic conductor, so we're thinking of diodes and light bulbs. You get a funny little graph where it curves, it kind of switches on at about 0.65 volts. And in reverse direction, pretty much nothing flows. And ohmic conductors, so like a resistor at a constant temperature, straight line graph of IV. Now, what's really weird is actually at GCSE, they often plot the graphs like this with the V across the bottom. Now, that's because that's the variable that you change in the experiment. However, if you plot them this way, the gradient is actually 1 over the resistance. So if I plot it the other way around, I put V up the y-axis and I on the x-axis, then the gradient, it will curve the other way, and the gradient is the resistance. So that's worth thinking about. So there you go. That's the main bits for energy and voltage.